Hello, and welcome to the second in our series of the Frontiers of Physics lecture series. Last fall, we had a lecture from Nobel laureate David Gross, who told us about particles and string theory and physics at the shortest distances. And next, May 14th, we'll have a talk on quantum computing, which will bring the most mind-bending concepts of quantum mechanics right in front of your face and make you think about what quantum information is, what a quantum book is, and how a quantum computer works. So the goal of this series is to bring the most exciting and most interesting new physics to the public, and to make it free and to make it accessible to people of all different backgrounds. I'm really excited that today we have a whole bunch of high school students who've coming, I believe, from Port Angeles and Sammamish. I'm looking forward to maybe 20 years from now sitting in the audience and hearing one of you give the talk. So if we had had this talk 50 years ago, you might have heard lectures on superconductivity, on a laser, on the transistor, on accelerators, on quarks. Some of these things have transformed what's in your pocket, your cell phone and your computer at home and a hearing aid. Other things have just changed how you look at stuff. So when I look at matter now, I think about all the quarks in there. And when I look at the sky, I think about the Big Bang and all sorts of things that have been discovered about the stars out there. So physics is really transformative. And today we're going to hear about one of the most exciting discoveries of recent years. In fact, it's literally the discovery of a century, the discovery of gravity waves 100 years after the prediction of Einstein. And this certainly will change the way we look at the skies. I can't predict whether 50 years from now we'll have two-way gravity wave wristwatches, but you never know. So normally when I introduce speakers to this series, it's a little dull. They went to a good school and they got a degree, and they went to another good school and got another degree, wrote some great papers, won a whole bunch of prizes. This is more interesting. Our speaker today, Professor Rainier Weiss, was born in Berlin, and the family escaped the Nazis and went to Prague, and then got out of Prague and came to the United States 2 months before the invasion of Prague. He was a refugee in the United States at a time when refugees were not very welcome. Does that sound familiar? He went to high school, but he was known to cut classes. He, more often than not, was going to a concert because he loved music. Then he went to MIT and he flunked out. I told you it was much more interesting than the standard one. Luckily, he met a mentor who took him under his wing and got him back on track and excited about research. And then it gets more like the standard track. He got a degree. He ended up being a postdoc at Princeton, which was the Center for Gravity Research in the 50s and 60s. He then went on to do wonderful experiments mapping out the microwave background radiation in the sky, the leftover fossil from the Big Bang, including the COBE experiment, which sent a satellite up into outer space and measured the temperature of the background radiation to incredible accuracy, and really confirmed the whole theory of the Big Bang and opened up a whole new set of questions. But today what we're going to hear about is the discovery of gravity waves, the observation of these incredible black holes whirling around each other 1 billion light years away. I'm not going to tell you any more about it because that's the subject of Dr. Weiss's lecture. Thank you.
Thank you very much. Wow. Well, it's indeed a pleasure to be here. And it's really quite an honor to be asked to give a talk in this place. Let me start by a little history first, and you'll see this interspersed into all of this. And that is that I'm going to tell you about Einstein's gravity, and the whole new theory of gravity that he invented. But you have to put it into the context of what he built on, and what you get taught in high school and in most physics courses that are the beginning physics courses, is you learn about Newton's theory. And why would Einstein bother with anything that was already working so beautifully? It got us to the moon. I mean, of course, Einstein was gone by the time we got to the moon, but it doesn't matter. Why would he bother to make another theory of gravity if you had a theory that worked so exceedingly well already? And that is part of the challenge here. What happened is that in 1905, when he discovered special relativity, he already realized, or the world realized, that there had to be some way to make things not instantaneous. In other words, information couldn't travel from one place to another, even in a gravitational field, instantaneously. And that kept him worried. And in fact, very shortly after the special theory of relativity got formulated, he began to think about gravity. How would you reformulate gravity so that it was consistent with the ideas of finite speeds of information, and also deal with the problems that change everything in physics when things go near the velocity of light, and we have very large masses and very large velocities. And that's what the origin of the general theory was. And he worked on that for many, many years. And by 1915, which is just about 100 years ago, he came and involved this very elegant theory that'd be named general relativity. It was really a new theory of gravity. And I want to give you a little feeling of that theory before we get started with gravitational waves. And the way you want to think about it is in this picture. This picture is, here you have to imagine a little first how Einstein must have thought about it. Imagine a network or a framework of poles you stick up like a jungle gym. I mean, many of you played in jungle gyms when you were kids. But where you make a thing which has 3 coordinates and you have bars that are all separated and they connect 1 meter apart everywhere. And that's sort of the way you imagine this and the way Einstein was thinking about it. And then he also, when you imagine this framework that's set up, you put a clock at every intersection point of the different bars that you've made. So you have a zillion clocks and you have to synchronize them all. And you do that by looking at them all and going with your clock and saying, oh yeah, let's set the time on each one as you go along. And that's what you set up. And now this picture shows what happens to that jungle gym, in effect, in the idea of Einstein's, the way he was thinking about gravity. Because here is some piece of the jungle gym, quite distorted. And by the way, there are clocks everywhere. They're not shown here. And they also get distorted in the following sense. They don't all keep the same time anymore. And what's happened is, here's the sun that's been put into this system. And you can see it changed the shape of space, but it also changed all the clocks as well. And here's the Earth, and it changed a little bit, the space around it, because it's not as big as the sun, not as big a mass. And this is, in fact, the conception that Einstein had of the way he was now going to look at gravity, and he wanted us to look at gravity. Namely, that what masses did is they distorted that beautiful Euclidean framework that you set up with the clocks that were all synchronized, and it screwed up the clocks and it screwed up the space. That's what it did. And now what happens is the curvatures in space and the reduction, the changes in the time, the clocks run more slowly near these big masses than they do for far away. Combine them with what the space now and the clocks together tell the Earth how to move around the sun. There's no longer a gravitational force. That's the big change. And in that framework, you can have gravitational waves. And I'll show you what they look like. They look like this. And they are generated by the same thing that the electromagnetic waves are generated by. Namely, these waves get generated by accelerated masses. You accelerate mass, you accelerate the sun, you accelerate anything, and it generates these gravitational waves. And it can't just be any old acceleration. It turns out spherically symmetric accelerations, things that are completely spherically symmetric, don't make gravitational waves. They have to look a little bit asymmetric. They have to have, in the fancy word of physics, they have to have a quadrupolar nature. Namely, a thing that two things crashing together, for example, will make gravitational waves. A balloon that expands uniformly and contracts uniformly will not make gravitational waves. Or things that are orbiting around each other, that sufficiently has enough quadrupole nature so that it will radiate. So it's a non-spherical acceleration that makes gravitational waves. And right in the first paper that he wrote, he said that these waves will move at the speed of light. They will move just the way as electromagnetic waves will. And here is what a gravitational wave will do. And I'll start this up in a minute. They're transverse waves, meaning if they travel at the velocity of light, they do their dirty work perpendicular to the direction in which they're moving. And now I want to turn on a little bit of an animation. You don't get dizzy with this, but the way you want to think about this animation, this is a picture of what a gravitational wave will do if you're standing here. If you can see this red square around that dot, well, these dots, think of them as places that label space, okay? And now what happens, you'll notice that this motion is sort of interesting. What it's doing is it's shrinking space in one dimension while it's contracting space in the other. And it keeps alternating that because it's an oscillating wave. It's coming in, it's either going into the screen or coming out at you, okay? And now there's another attribute of this thing which is very important to recognize, which is critical in the business of being able to see how you might detect these waves. And that is that you'll notice that, let's say, take you again. Here you are. And here, these two dots right there don't move as much as this dot and that dot. In other words, the amount of motion of those dots is a function of how far they're separated. And that picture then, at any one instant, is a picture of constant strain. And most engineers know what a strain is. I mean, you experience that when you pull a rubber band. And in fact, if you want to show this to your kids, just do the following. Take a rubber band and not stretch it, and put every quarter of an inch or whatever, every centimeter, make a little mark on the rubber band and pull it apart. And when you do that, that is also a motion of constant strain. And what does that mean? It's the change of the position of an object is proportional to their separation, or the change of the position divided by their separation is a constant at any one moment in this picture. So the field quantity, the quantity that you want to be looking at, the thing that tells you about the strength of a gravitational wave, is the strain. And we'll talk about that a lot more in a minute. So I'll stop this thing. And in 1916, in 1915, he wrote these wonderful equations, which were, in fact, the Einstein field equations, which, as I said, we celebrated last year. In 1916, he wrote another paper in which he does what's called an approximation calculation. The huge field equations he had were very complicated to solve. People really only know how to solve them now with computers. I mean, they can do it completely. But what Einstein did is, all of us would do, he tried to make it so that you make it linear, looked at the gravity when it was small, and that was what he did in the 1916 paper. And in that paper, he showed a whole bunch of different things. He showed what I just told you, the gravitational waves, and he says something really quite remarkable in that paper. It was in German, of course. And what it says, what this is I'm not trying to ask you to understand the equation. I want to tell you what it is. It's that here is a change in the aspect of something which is moving, and here he's trying to calculate how much power is moved, how much energy is being taken out of the system, and effectively per time by this motion. And he says in here in German, which those of you who can read German will read, but here's a translation of it. He says this quantity A, so in any case one can think of A, that thing, will have practically a vanishing value. In other words, he says put the numbers into this thing, evaluate the equation, and you will find out it's absolutely zilch. It doesn't do anything. And now I've asked people who have been experts in the science papers of Einstein, and there are a whole bunch of people who do science history, to find the place where he did these back-of-the-envelope calculations where he might have come up with this statement. And they haven't been able to find it. I mean, you don't find it in his notebooks, and you don't find the back of envelopes anymore. So there's no record of it. So I took a very presumptive step and made myself Einstein for the moment of this lecture. And he must have done both of these things is what he might have done. For example, he might have considered two trains colliding with each other. That's something they could have imagined in 1916. And here is a formula which I'll just describe what is in here. And this is so you and I both can estimate anything we want about gravitational waves. You don't need any more than this. What is in this formula is h, which is actually the strain. That is the strain. H is a symbol he used for that. And what is it proportional to? It's proportional to things you know. For example, this is g, which is the constant you'll find in Newton's equations also. It's the strength of gravity. It's the mass of the system that's doing the colliding or the motion. It's divided by the distance you're away from the source. That's the distance you're away from the source. And it's divided by c squared, which is the velocity of light squared. That quantity, that right there, the gm divided by r c squared, that quantity is a very important quantity. It gives you the strength of gravity in an absolute way. You and I, all live in a place where that gm over rc squared is about 10 to the minus 10. Now, those of you who don't know exponential notation, I'll be using it a lot. When I say 10 to minus 10, I mean it's a decimal point with 9 zeros and a 1. Okay, that's what I mean by 10 to the minus 10. You're going to have to live with that. I don't want to get it right and say point, I don't want, that's just too boring. 10 to the minus 10 is a wonderful way to encapsulate that, so you'll have to live with it. And so it turns out, at a black hole, which we'll talk about later as we get into this thing, that number is 1 at the edge of a black hole, at the place we'll talk about later. And so Einstein's equations work over a dramatic range of strengths, field strengths. Certainly, you and I live in 10 minus 10, and a black hole is 1. People are doing experiments here in Adelberger's group where that is even smaller, 10 to the minus 5 of 10 to the minus 10. So 10 to the minus 15. It's a huge range of gravitational field strengths, and those equations that he saw and pure thinking in 1915 work over that huge range of energies. So that's the first piece of making H. And then what's in here is the velocity of what's doing the moving divided by the velocity squared divided by c squared. So let's just put some numbers into that formula using, for example, what Einstein must have done. Here's 2 trains that have smashed into each other. And let's pick them as having about 10 to the 5 kilograms each. That's the mass that's moving. Even, well, nowadays, we probably don't go that fast with trains anymore because we don't know how to make trains anymore. But in 1916, they probably went at 100 kilometers per hour, okay? You put that in, and the collision took 1/3 of a second. That's not completely crazy. And you have to go far enough away to see this radiation. You can't, because if you're too close to it, you'll see Newton. That's all you'll see. But you go far enough away, you'll see Einstein. And you have to go out in a range and distance far enough away so that you can see the radiation itself. So you have to go 300 kilometers. That's about with these numbers. And what you wind up with is a strain that's 10 to the minus 42. Now, that is truly a small number. That's infinitesimal. Okay? That's point, I'll just say it one more time. That's a point with 41 zeros and then a 1. Okay? It's just vanishing. So no wonder he made a statement like that, this will never have any significance. So the other thing he might have thought about is, well, let's look at things that, not try to measure something that's on the Earth, but there must be systems that, like the binary star system, and we'll see those a lot in a minute. And in his day, there were known binary star systems that sort of had masses of 1 solar mass each. They had an orbit that took 1 day for them to go around. Now, he probably didn't know about the galaxy. Nobody knew about the galaxy, but let's put it at the center of a galaxy. That's 10 kilo light years away, okay? 10,000 light years away. And then you get a strain, which is actually, it's still a mighty tiny number, 10 to the minus 23, with a period of half a day period. It's twice the frequency of that. And, but that is, as you'll see when we get talking about real gravitational waves, is not a tiny number anymore. But the way he couldn't have measured it, but he could have maybe looked at the thing and watched it through a telescope. That was probably the thing he might have thought of. And how long would it take so that you could see that this was losing energy to gravitational waves? That's something he could have done. And so he would have wound up with something that took 10 to the 13 years before these 2 stars got half the distance between them. That's how, when you lose gravitational energy with 2 things that are going around each other, and we've been talking a lot about that, 2 things going around each other, there's a very persnickety thing that happens. They go around each other, but they get faster and faster as they get closer and closer. That's what they do. And so you would have seen, he would have calculated, that took 10 to the 13 years. That's more than the age of the universe, although the universe was not known about in those days. So it looked pretty hopeless. It really did. And I don't blame him for writing that very negative and dismissive sentence. So what's happened since? 2 things have happened since. Technology has changed dramatically. And the other thing that's changed is discoveries in astronomy. And I'll show you one that is most important. And by the way, I just want to correct something that David said, which is it's perfectly fair that he should say it. We were not, this is now LIGO, was not the first to ever get real evidence for gravitational waves experimentally. It's these people. And these people, this is a graduate student at the University of Massachusetts, Richard Russell Holtz, and here this was a professor at the University of Massachusetts in Amherst. They both now at Princeton. This is Joe Taylor, and they did something really amazing. I think to me it's as wonderful as any other thing that ever was done in astronomy. What they did is they found, and here's how they did it. They found it by using radio telescopes. You don't see a thing with a radio telescope. You can hear things with a radio telescope, but you can't see it, you know? And so they listened, and they found a place where they found something that was going brrr like that 17 times a second. And that was this thing. It's a pulsar. It's a neutron star. They found this. That's in a search they were doing for neutron stars all over our galaxy. But this one was kind of strange, because what it would do, it would go 17 times a second. It would get a light pulse, or radio pulse would go and hit the radio antenna. And then sometimes it would be a little faster than that, and sometimes it would be a little slower. In other words, as this thing was moving toward us, or the radio dish, it would be a little faster. When it was moving away from the radio dish, it was going a little slower. Much the same as when you hear a cop car, you know, following you, and as they pass you on the highway, it's a high-frequency siren as they're coming at you, and then when they move away from you, it's a low frequency. It's a Doppler effect. Most of you know about that. So they divined from that, just from listening to the pulses from this thing. That's all they had. They couldn't see a damn thing. They decided it had to be another star that was going around it. And so these two things were going around each other. And what they discovered very quickly, it took them, and this is the time, this is sort of talk about persistence in doing science. They found this thing in 1973, and they were still working on it in 2000. And they kept following this star system on with the radio telescope, and they found out that indeed they could solve all from just the way the pulses came in and they changed. They could find the masses of the two stars. They could find out that the thing was moving around, that the ellipse that this ellipse they have was actually turning, which is what you expect in general relativity. They could see the bending of the radio waves from that star as that one was getting in its way. And most important, they discovered that this system was speeding up. In other words, what was happening was this time of going once around every 8 hours was getting shorter and shorter. And that's what this picture, that plot is all about. This is epic. This is, time, evolved time since 1975 to 2000. And this is the change in the time it takes to make one revolution. And it's getting shorter and shorter. You see there's negative signs here. It's getting shorter and shorter. And the dots that they have here, those are the dots that they measured of the change in the period of the orbit. It's getting shorter. And this is the theoretical curve if this thing was losing energy due to gravitational waves. I mean, it's a dead ringer for it. And that was, as far as I'm concerned, the first real evidence that there were gravitational waves. And it was a very important moment because there had been endless discussions in scientific community about whether the gravitational waves that Einstein had predicted were real or not. People made calculations, sometimes some people, even Einstein himself in 1936, had come up with a calculation with another scientist. They published it wrongly. They made a mistake, but that happens all the time. And they said, no, gravitational waves, they had to come to the decision that gravitational waves were just not real. They didn't carry any energy, they didn't carry any momentum, they didn't behave in any way physically sensible. And then later on, people began to doubt this, and it took until actually this experiment to really prove that gravitational waves carry energy. There was endless discussions about this. Okay, so the next step in all of this is a little earlier than what I just showed you, but it's as important. This man is Joe Weber, and he was a member of a meeting in 1957 called the Chapel Hill Conference of General Relativity, in which people were really discussing this issue, and a lot of very famous people were there. Dick Feynman was there. He, in fact, listened to the whole conference for a while and said, "This is all mathematics. You guys got to do some physics. Get to it." And but they did get to physics, and I'll talk a little more about that as I go along. And one of the things they got to is that Joe Weber and John Wheeler, who was a physicist at Princeton, came up with the idea that maybe one ought to detect gravitational waves by that picture that I showed you, that stretching of space. It turns out the way they reasoned it, it also looked like there would be a force, a differential force that a gravitational wave would make on matter. And what they invented was this thing. Now, the guy in the picture is Joe Weber, and he was a standard man, not, I think, 5'10" or something like that. This is a gigantic piece of aluminum. And the idea was, and you see him before I tell you the idea, what he's doing there, he's soldering to that big piece of aluminum, he's soldering little strain sensors, things that will give a voltage out when that bar starts singing and starts moving. And so the idea was that a gravitational wave would come along, go through the bar, and stretch it a little bit, compress it this way, stretch it that way, and that would start the thing ringing, and it would ring on just as though it had been hit by a hammer. It was a very straightforward idea. It was not such a clever idea to think about how it worked. That was a problem for me, by the way, as we'll get to later. But on the other hand, so what happened is Joe set this up. This is Joe Weber, and he set this up in his lab in University of Maryland, and then he had another one of these in a golf course 8 miles away, and he kept seeing things that were coincident. And he saw something of the order of 100 events per day that were coincident between his bar in the lab around his office and that place he had set up in the golf course 8 miles away. And he got very interested in that. And of course, he didn't say it was gravitational waves right away. But what made him say that was a third piece he did. He took another one of these bars and put it in Argonne Laboratory in Chicago, which is about 800 miles away from Maryland. And then he had 3 things to look at. And those 3 things would give coincidences on the average of 1 or 2 per day. And in 1969, he published a really quite dramatic paper saying he had looked at everything that could do this, and he was now convinced that he had detected Einsteinian gravitational waves. And that caused the whole world, a lot of people, to at least 4 groups in the United States, a group in Russia, several groups in Europe, to start doing the experiments. And by 1972, most people weren't seeing anything. And that was a very big blow to everybody. I mean, he had made a very dramatic claim. A lot of people did it exactly the way he did it, and they saw nothing. There were some people who did it better than he did, and they didn't see anything. And that was a serious issue. And I was at that moment asked to teach, not at that moment, but about a little earlier than that, I was asked to teach a course about general relativity at MIT. As I explained to David, what happened is that I had started a lab at MIT on gravitation and cosmology, which were topics that I thought were interesting. Nobody was working on that at MIT at the time, and that field had been relegated to mathematics, and it looked sort of not interesting to physicists. And so they asked me to teach. The head of the department came to me and asked me to teach a course in general relativity. Of course, I didn't know any general relativity. I mean, that's, what I knew, I knew a lot about the experiments, but I didn't know hardly any of the mathematics. I didn't know tensor analysis. I didn't know any of the fancy stuff you really had to do. But I couldn't say I didn't know it, okay? So I was sort of in a situation where I was a day ahead of the students. Most of the time, I was a day behind the students. It didn't matter. But anyway, so we had, thank God, a set of convivial students who were willing to let this somewhat blustering character allow them to teach them. But nevertheless, we got along. And in the middle of it, they asked me about Joe Weber's experiments. Now, this is before he made his big statement, but it was close to the same time. He was already at that time giving talks at physical society meetings, saying that he was implying that he was seeing something that looked like gravitational waves. He didn't finally have the courage until 1960. The course was in 68 and 67, and his big statement was in 69. And so I had a problem. And when the students asked me, explain to us how a gravitational wave interacts with one of Weber's bars. And I couldn't really do it because I didn't believe it. I didn't understand how the wave actually pushed on the bar. That was my problem. I thought, here was my problem. I'd been so deeply immersed now in learning general relativity that I felt there were no more forces. Forces were an artifact of Newton. And I want to see how this thing worked geometrically. And it was such a beautiful idea to do this all geometrically like I described to you. And here was this thing, very ugly thing that was being pushing a bar around. Didn't seem right to me. So I wanted to explain this some way in a geometric way. And so I spent the weekend thinking about that. And I came up with something which later turned out to be reasonably important. And it was, why don't I explain it as put a mass, one of those spots, those dots I showed you, put that over here and give it a clock, and put another one over here and give it a clock. and then send a light signal from this mass to that one and have it reflected and come back to this mass. So I do all my measurements all in one place. I don't get messed up with having to worry about how you transfer measurements from one place to the other. It's all done in here. Send the light beam back, come back, and you measure the time it took for the light beam to come back and forth. Okay? Very straightforward problem. You can do it just like special relativity. It's a simple problem to pose. And now what happens, along comes a gravitational wave down on this system, and what it does is it changes that time. And that was, it's shorter and longer than it was without the gravitational wave there. Looks so gosh darn obvious to me, okay? And so I gave it as a problem, and everybody did the problem, and they all got the right answer, and everybody went away happy, and that was it. Okay. I put it aside, I didn't think about it anymore. And then when 72 came around, and nobody had seen any of this, I began to think about this as a more serious thing. It was, let's put it this way, Einstein would have called that a Gedanken experiment, the one in that, the thing in the teaching the course, but I want to convert that Gedanken experiment into a real apparatus. That's a very different thing. And so let me give you the germ of the idea, and that's what this little animation will show you. So what you're seeing here is you're seeing a laser. That's not a laser, but think of it as a laser, okay? And it'll send out a light beam hitting this beam splitter, which is a device that splits the light, so half of it goes to that mirror as transmitted, and half of it goes to this reflected. And then the lights come back to this thing, and here's a photodetector. And let's see what happens if you make it so that the light spends exactly equal time in this arm and that arm. By the way, those of you who know, this is called a Michelson interferometer. It was designed back in the 1800s, okay? So here's what happens. Yeah, it works, wonderful. And so here's a light beam, but now the red shows where the intensity of the light is, but this wiggly thing is the electric field in the light. It bounces from the light, bounces from these mirrors, and now you'll notice that if these times are the same, the two fields cancel each other, and there's no red here, there's no light hitting the photodetector. And now what happens is the animation will start moving this mirror one way and this guy in and out. So there's this push-pull thing that's going on. That went on in that. And you'll notice that every once in a while there is light at the photodetector, especially when you have moved those mirrors. And by the way, what you've now done is you've made one arm a little longer and another arm a little shorter. And now all of a sudden that cancellation, which gave you no light at the photodetector, is spoiled. It's very straightforward, and that is the basis of the whole idea. There's no more than that. Okay? That is the idea for how you detect gravitational waves. Now, the trouble is, when you get to actually wanting to do it, okay, you get into a problem, which is the following. And we didn't know that at the time, and neither did Joe Weber. Joe Weber, if you want to know what he was detecting a strain which later we figured out was about 10 to the minus 14. Now, that's what he was measuring. And by the way, later on, people made the calculation that if he had been right, he would have wiped out the galaxy, our galaxy, in about 1 million years. In other words, you would have converted every mass in the galaxy into a gravitational wave energy to get such a strong amount of strain. So that was another, you wouldn't, as a theorist, you could argue that Weber was seeing nothing. I much prefer that other people who were doing experiments were seeing nothing. That would be, okay. So, but this is when people like Kip Thorne and a lot of other people began to really calculate what kind of gravitational waves you might expect and how strong they might be. The number that they felt you had to get to, that value of h you had to get to was 10 to the minus 21 and smaller. Now, when you convert that into the dots in that picture being 4 kilometers apart, which they will be in LIGO when we get to LIGO, that means that the motion that you're talking about at the endpoints, those dots that were moving quite violently when you had that animation, is only about 4 times 10 to the minus 18 meters. Now I want to give you a little feel for 4 times 10 to the minus 18 meters. And that's important that you understand this. That's when the fat gets in the fire. It's not in the idea. The idea is simple. But now what you have to do is let me give you first a feel for it. So you start with a meter. In the United States, we don't deal with meters, we deal with 3 feet, okay? It's close enough. And so you divide by the first 10,000 and you get a hair, okay? That's easy because we all have hair, most of us do. And then you divide that again by another 100 and you get to about 1 micron, or a visible light, which is about half a micron, or 10 to the minus 6 of a meter. And you still can experience that. You can do beautiful things by looking at a light through a pair of fingers, and you'll see little bands. It's very easy for you to establish that light has a wavelength of about a micron, or half a micron. You can even get to the next step here, which is that divide by the next 10,000. You get to the size of an atom. And you can prove to yourself and your kids how big an atom is. It's real easy. The way you do that, that's about as far as we can go, though, that you can prove to yourself. You take a medicine dropper, and put a little bit of oily stuff in there. I don't care what, oily, any vinegar, oil, or peanut oil, whatever you like. Or gasoline. I don't advise that, but that'll work too. And then you look at the medicine dropper drop, and you measure it as best as you can with a ruler, or maybe millimeter in diameter, whatever it is, and you can calculate the volume of the drop. That's real simple. You measure that because you know a little arithmetic. You know how to get from the dimensions of the diameter, you know how to calculate the volume. And then you drop it into a bucket, or into the bathtub, or into the sink. It's just full of water. And you'll notice as you drop it in, it spreads out. And you'll see the edge because the colors are different in the water. And you measure it with a ruler. You measure sort of the size of the area. You do that. And then you need one other thing. How high is that thing? And that's going to be 1 or 2 atoms. So that's still something within your capability. And and you'll find out that when you do the calculation, it's a nice experiment to do. You should do that with every kid in the world. It's just a great thing to do. Then you wind up with 10 to the minus 10 meters for the size of an atom. Not 1, 2, order 10 to the minus 10. Now you get into the regimes which most people can't experience directly, and you have to divide by another 100,000, and you get to the nuclear diameter. That's the nucleus inside of an atom, and you're still not there. You have to divide that by 1,000. And then you get to this 10 to the minus 18. And that's where the challenge is. And there are 2 challenges in this business that you can get to, and I'll tell you exactly what they are right now. The first challenge is you're going to be using light to make that measurement. And light has a wavelength of about 10 to the minus 6 meters. You have to get to 10 to the minus 18 meters. So you have 10 to the 12, a billion, no, I don't know the damn numbers, a million times a million, whatever that is. 10 to the 12, you have a factor of 10 to the 12 to go to do the experiment. That's your first challenge. And that's to measure with light such a small motion. But then you have another challenge. When you get done, that those 2 objects that you have that are going to be measured to that precision can't be standing, they have to stand still enough. They can't be wiggling for other reasons besides the gravitational wave. And we'll talk about that a lot more in a minute. So first let me talk, both of those things turn out to be factors when we get done with it. And I'll get more to it in a minute. Those are both 10 to the 12 factors. We'll get to that. And that's where the challenge lies. And that's why it took 40 years to get there. Okay, so here are the people who actually made the first challenge work. This is the business of going from 1 times 10 to the minus 6, 10 to the minus 6 meters, to 10 to the minus 18 meters, using light as the way to do it. And there was a group at MIT, and there's this is the man actually over here, F.A.E. Pirani, who at that meeting in 1957 finally settled the argument. What could you do? How could you measure a gravitational wave? And he came up with a very neat way of not necessarily showing us that. He showed us how, if you take 2 particles moving in that jungle gym that I showed you earlier, and they're moving along a path, that's the easiest path for them to move, the straightest line they can go on. In the fancy words of that field, those are called geodesics, the shortest paths in time and space that something travels. And you want to measure the distance between those things. You can do it in a way that is absolutely correct. And that's what he showed us, F.A.E. Pirani showed us. And based on that, I came up with, using that Gedanken experiment, turned it into a real experiment. And here are the basic ideas. I won't go through this diagram. I'll go to a more easy diagram to understand. But these are the principal ideas, and I'll show you better in a minute. But you make a device, there's a laser here, and one of the ideas was to float all these masses. They're all hanging. You don't do that with interferometers. People never did that before. They just don't hang. You don't hang interferometers. People put them on engine blocks to make sure nothing moves. Okay? So you hang all these masses, and the other thing is you let the You take the light and let it bounce many times between the two. You build up the sensitivity apparatus that way. And the other thing is that you use a laser for the interferometer. That's not new, but in those days it was new. So that was a thing that was built at MIT. And we got some distance with that, but then a group in Europe, and the first group in Europe that really was, I mean, much better work than we did at MIT. They did a really beautiful job. And they had money, they had a lot of good, skilled people, was a group that was a group at the Max Planck that was run by Heinz Billings. And you can see him here. He was a computer engineer, this man. He invented magnetic core memory along with other people. And that's how he got support from the Max Planck Society. But he got interested in this idea of Weber's. And so you can see here is his bar. And he had worked on this thing. And he and a group in Italy were really one of the best people to show that Weber was wrong. They saw absolutely nothing. And they proved it to us. So they decided what should they do next. And many of them said, let's make cold bars or do the next thing. But no, several in the group had read stuff that we were doing, and they said, why don't we do what the guys at MIT are doing, which is fine. And they did a much better job than we did initially, and these people all contributed. In fact, I'll just say what they are. We'll get back to that, but you'll see the drawing. But they contributed different ideas. For example, that the idea you make cavities. Now, this is the idea that you recycle light. We'll talk about that in a minute. That you hang every mass in the system. That you know how to do the optics right. And this, Lisa Schnupp was the person who came up with a very clever way of reading out the fringe, in the light fringe in the interferometer. Along with that was a group in Scotland. Now, they were first in Europe, but then a group in Scotland who had gone through the same history. They also had made a bar, found nothing, and they decided that interferometry might be a better way to do this. And this is a group around Ronald Drever, who then moved to Caltech after this. But his group invented various ideas. For example, Harry Ward invented a way how you align the mirrors, how you keep them aligned. Brian Mears came up with a very clever idea I'll show you in a minute, which is to add another mirror to the interferometer to change its spectral response. We'll talk about that. And then Jim Hufford just ran the group when Ron Drever left. He was a young man. All of these were students of Ron's. And so this is the group back in the 70s that actually came up with most of the ideas that went into LIGO. Okay? And this is actually the instrument that was built for LIGO that we built. And this is a schematic of it. And I'll show you the different pieces of it so now you know a little bit about the interferometry from that animation. And I'll dwell a little on this. So here's the things you know about already. Here's the laser. There's the beam splitter. And there are these end masses that respond to the gravitational wave, if you want to choose them at that. They're doing the moving. Now you'll notice a whole bunch of other mirrors in here. Let's start with more simple parts of this. This mirror here makes this into an optical cavity. In other words, it is used to make the light bounce back and forth many times. And the same thing happens on this side. And what you do, you endeavor to do exactly what we did in that animation. You make it so they spend equal time. The light spends equal time doing the bouncing back and forth here as bouncing back and forth here. And as it leaks out of the system, the amount of change, well, the time that is spent is the same. So you come to the beam splitter, and here's the photodetector. So now here are these two mirrors we had said nothing about yet. This is the first one. That's much easier to explain than the other. This mirror that Schilling invented, as well as Ron Drever, is an idea that is pretty straightforward when you see in a minute how the ideas work. Remember, I told you that none of the light goes to the photodetector when you set this thing up. It's only when a gravitational wave comes along and moves this mirror in and that mirror out a little bit that you begin to see light at the photodetector. So where is the light going in that interferometer? The light's coming out of the laser, and it turns out it's not going to the detector, so it's all going back to the laser. That's what it does. Every bit of the light, except for what's absorbed by the mirrors. So what next is the idea was then to put a mirror right there. And if you put that mirror at the right place, and you make the transmission of the mirror just right, you have to know what to do what you're doing, you can do something very interesting. You can make it so that all the light that comes out of the laser, when there's nothing going to the photodetector, all the light comes out of the laser, goes through that mirror, and gets trapped in this system, and nothing goes back to the laser ever. And you do that by doing another interferometer between the light that would be coming back from the interferometer, going through this mirror, going toward the laser, and canceling that with a light that would go from the laser and be reflected by that mirror. There are two beams there that are going in the same direction, and you can cancel them by doing an interferometer again. So that's called a power recycling mirror, very elegant idea. And that effectively takes the interferometer and makes it as though you have a bigger laser here. So what that does, for example, in advanced LIGO, you might get 25 watts out of the laser. In this little piece of the interferometer, there's no light ever going here. Forget about that. But there's something like 500 watts of light going around inside here. And then in here, there's a megawatt of light going back and forth. Megawatt, or maybe 3/4 of a megawatt. So you've done a very elegant thing with that mirror. You've trapped the light, and it only goes into the interferometer. And where does the stuff go? It goes to heating the mirrors. That's what it does. And that becomes a problem after a while. So that is this other mirror, which is actually much harder to explain. And what that mirror does is it takes the light that is there when these have been moved, and it takes it and it can reflect it back into the interferometer. And what I want not explain it. If you ask me questions about it later, I come to the stage later and talk about it, I'll tell you exactly how this works with another diagram. But you can change the way the interferometer spectrum works. In other words, how sensitive it is at each frequency by putting that mirror in. And in the initial interferometer, we didn't have that mirror. Where we ran LIGO for about 5 years, we didn't have that. That's now incorporated in advanced LIGO. Okay, so next step in this thing is getting advanced LIGO going. And advanced LIGO was a big deal. It was a $200 million project just to build it. And we'll talk about where it went, but you had 2 detectors, both 4-kilometer arms. The arms on those things were 4 kilometers. Very much the same as that drawing that I just showed you, the schematic, but with other things now which we have to be incorporated that reduce the motion of the mirrors, and we haven't talked about that yet. But this is the group, and why I want to show this slide. It tells you some interesting things about a big project. First of all, it turns out that Drever, there he is, and Kip Thorne and I tried to run this project, and we didn't know how to do it right. So it turns out that many committees said, you guys flunk. And we got a director named Robbie Vogt, who was an ex-provost of Caltech, who was a bit of a dictator, but he had the right instincts about how to get this thing going. And he got us through writing one of the most remarkable proposals that ever were written. It's a beautiful textbook on all the stuff that was in our heads that we hadn't written up. And we wrote it up. It took us almost a year to write this proposal. But it got the acceptance of the reviewers, and it got us the initial bunch of money to start building LIGO. And one of the clever things that Robbie Vogt did is he coupled, because his idea was, this is a very complicated engineering job to build this thing, and you better get the scientists who know what the complexities are mixed up with the engineers who know how to do it. Don't make engineers build something without scientific advice. And that's what he did for all the different contracts. For example, this group of people, well, these two, and I was the guy who worked with this guy, there was always a scientist mixed up with an engineer. For example, this is for the physical construction. This was for the vacuum system. And I worked with Larry Jones for the thing that was a very special piece of the vacuum, namely those big, long beam tubes, how to build them cheap enough so we could afford LIGO. And that was a very clever idea that Robbie Vogt had. So now I want to show you the very first detector that we built in LIGO and what the noise budget, what kind of things disturb it. And then you'll understand where the second piece of the hard problem comes from. Now, this is a somewhat complicated drawing. This drawing has frequency down here, and it has strain here. For example, this is 10 to the minus 25, 10 to the minus 23, 10 to the minus 21, 10 to the minus 19, if you can't read it back there. But it's not strain directly. It's the spectrum of the strain. It's how much strain per bandwidth. And now, the way to convert that into what I've just been telling you is to say, look, let's look at this point in the picture. Here's the performance curve for LIGO, the initial LIGO we built. And I'll explain a little bit what these curves mean in a minute. But right now, let's just take this point down in here someplace. It reads 10 to the minus 23, everything about here is 10 to the minus 23 strain per root hertz. And then you look at the frequency, and if you take a bandwidth that's equal to the frequency, you wind up with a factor of 100, but it's per square root of that, so it's 10. So you wind up that the best this instrument was doing is about 10 to the minus 22 It's 10 times 10 to the minus 23 in the strain that I was talking about with you earlier. That's how you make the conversion. But this is a way of showing how the spectrum depends on frequency. And for example, this piece, the thing up at high frequencies here, is determined by how well you can make the phase measurement of the light. And you need more photons. The more photons you have, the more light particles, the more power you have in the light, the better you can do this. So this will go down if we increase the laser power. On the other side of this thing, which is not important in this instrument, there's something very interesting. It's something called radiation pressure noise. And what is that? It becomes important in the advanced detector. What that is that if you try to increase the power, so you reduce this, it turns out this line is due to the fact that as you increase the power, you start pushing the mirror around. And the photons actually start pushing the mirror around with some noise. And that is, for those of you who know a little quantum theory, the Heisenberg microscope. All over. That was how the uncertainty relationship was developed. In other words, now you're talking about the Heisenberg uncertainty principle with a thing that is sort of 20 kilograms. That's what the mirrors were here. And quantum mechanics becomes important in this system because you're looking at such a very small motion. So we had to include that. Now, it isn't a big deal yet. But if you increase the light, this will go down, but this will go up, and eventually you can't just keep increasing the light forever. So that was not a problem in the detector, as I said, but you have to put that in a curve. What was a problem is here. This is another limit. And what that is due to is just the simple idea that hanging these pendula, handing these masses by pendula, was the pendula move because they're at room temperature. They get kicked around by thermal motions. They're just at room temperature. We didn't cool the thing at lower temperature. So everything that's operating at finite temperature has fluctuations in the position, just like an atom does, except now we're talking about big mirrors. So this is the thermal noise. And then finally, here's the thing that really cost us most of the time, and that is that you're living in an Earth, and that's where that factor of 10 to the 12 comes. You're living in an Earth right here, right in this room. You're jumping up and down by a few microns, by a few times 10 to the minus 6 meters, and you have nothing to say about it. That's the Earth shaking and doing this stuff, and the atmosphere jiggling the Earth, and it's the oceans making waves. It's every conceivable thing that shakes the world. And that you have to deal with whenever you make a very precision experiment. And so one of the things we spent a lot of time on is reducing this noise by doing isolation systems. And I'll show you what we now have. I don't want to spend a lot of time on it, but that was a big problem. Now, the remaining pictures here are things that cost money. For example, this curve right here, which is what we attained, is just due to, you have these 4-kilometer tubes, and you send a laser beam down that tube, and there's not a perfect vacuum there. So atoms and molecules get in the column of gas, get in the column of the laser. And what they keep doing is, every time you put another atom in it, it makes a little wave of its own. It re-radiates that, and that's called the index of refraction of the gas. And that's fluctuating because the number of atoms in the column isn't always the same. So you do that, the way to get rid of it, you make a very good vacuum, and that costs a lot of money. So that's where the money went. And then lastly, there's one I want to talk about, is this curve right here. And that curve is one which isn't so straightforward and isn't so easy to understand, but becomes extremely important as we go on in this field. And in fact, is the basis for doing this in space, which people are doing. And what that is due to the fact that the ground is also interacting with the masses in a different way than just shaking it. What it's doing is the ground, waves in the ground, have changes in density of the ground. So a ground wave will come along, and here, let's say this is the mirror. And so here's a wave coming in the ground, it's squishing the ground, so the density of the ground is a little higher here than it was before, and here it's a little less, and it's a little higher again, and so forth. And that extra amount of mass that's squished here pulls on that mirror, just like by gravity. And the same thing is happening in the atmosphere. The atmosphere has fluctuations in the density of the atmosphere, and they pull on that mirror, and you can't shield that. So that's why we call that gravity gradients, okay? And these things have this incredibly fast slope. See how quickly that grows as a function of frequency. And it gets very serious. You can do, in fact, if you do a little bit of improvement, it still is a terrible, you have a huge barrier. That's almost like a huge barrier to being able to do it. And that's why people, as I said earlier, are going to try to do this in space. Now, I'll show you what we did in advanced LIGO. to make this better than that picture. First thing is, and this is an idea that came from the LIGO is not just MIT and Caltech. It's a whole bunch of people who are part of the LIGO collaboration. I'll show you that in a minute at the end. But this is a design that was built by the Scots, the people who were Ron Drever's group in Scotland. And this is the suspension system they gave to LIGO. And what it is a whole bunch of pendula in series. That's the mirror, which is doing the reflecting of the light, but then it's hung from another mass. And that's one pendulum. Then this mass is hung from another mass. That's this one. That's another second pendulum. And that mass is hung, this mass is hung by that mass. So there are 4 pendula, all in series here. And then they're all, here's where they attach to the ground. These are springs. And so consequently, each pendulum gets you a reduction by the 1 over the square of the frequency. And so you get a huge attenuation of the motion of the ground. But that's not enough. The thing that, and this is something I don't think I want to sell you as a thing for your labs. It's a very delicate thing. But the next thing, I think if you have a delicate experiment, you may want to think about. And that is this thing here, which I won't describe except to tell you it. Here's that pendulum, that multi-pedaled pendulum, and it's hanging, there it is, and it's hanging for something up here, which is a seismic isolation stage, which has a very clever idea in it. The idea is, here is a seismometer, which is a device that measures ground motion. Okay? And you mount that on a platform, and then you push the platform around, there are pushers on this thing, that make it so that the seismometer goes to a 0. In other words, if the Earth wants to go up, it pushes the platform down. It's the same thing as many of you have had earphones, have headsets that eliminate the sound coming from the outside world so you can hear the music without the disturbance. How many of you, just raise your hand if you've played with those in your life. Yeah, many of you know this. Okay, it's the same principle. It's called a feedback system that kills the noise by measuring the noise. And that's what this is. It has 2 stages in it. And by the way, we'll get to it. Those 2 things, this and that, are the thing that made it possible for our detection. That's the big things that made the difference. And here, then, is the new curve. It looks a little different. This is advanced LIGO, the same kind of curve. And here is a frequency. This is 100 hertz, 10 hertz, 1,000 hertz. And here is a strain spectral density again. Here's 10 to the minus 23. And you'll notice here is the curve for the performance of the instrument. We haven't made it, as you'll see in a minute. We're not quite there. We have a lot to learn yet. But there's already a known noise term that's going to cause us a lot of trouble. And what that is sort of amazing. It turns out it's the thermal noise in the coatings on the mirror. We've got to solve that problem if we're going to try to make the thing better. So, now I'll take you some real data, and then I'll show you the discovery. Okay? This has all been about the instrument. But this is actually quite noteworthy, so I want to show you what this is. This is the same curves, but now with real data in them. In other words, this is frequency. Here's 10 hertz, 100 hertz, kilohertz, 10 kilohertz. And here's 10 to the minus, I can't read it so well, 10 to the minus 24, 10 to the minus 23. So let's start right up here. And this red curve, which is real performance data, okay, does this. And that is the Virgo detector, which is an Italian-French detector, which was operating in during the initial times with LIGO together. And that was their sensitivity curve. Here is the initial sensitivity curve for LIGO, and it is this purple thing. And it goes like that. It gets worse at low frequencies here. In fact, Virgo is better than LIGO at that low frequencies. And this is what we ran, that combination of curves ran for 5 years. And we saw nothing. We saw absolutely no sources whatsoever. Okay? It ran from 2005 to about 2010. And then we began to build advanced LIGO. And this is, in fact, the spectrum that made the detection you're going to hear about, this green one. And you'll see something interesting about it. There's a huge difference right in here. Here's the green curve, and there is the purple curve up here. That's a factor of almost 100. Right in here is where the black holes that we detected live. They live in there. And if we hadn't made that huge change at low frequencies, we would have detected nothing. That's important. Now, let me show you the other thing that's important. Here's the theoretical curve. That line right there, that light turquoise line, that's in this thing. That's the theoretical curve for the operating conditions of that instrument. And you can see there's a big discrepancy between the green line and the turquoise line, right in this region here. It gets bigger and bigger. And what happens, we don't understand that yet. There's a mystery noise we do not understand in the instrument. And so that's why we quit running. We want to find out more about that. We still are not there. And here's the best we hope to get. This is the very best performance we hope to get in this instrument as designed. That's the dark blue line here. It's a good bit down still from there, a factor of about 2.5. And there it is. And here is a curve that Virgo hopes to get when they get on the air again. And they want to be running with us. And they're equally sensitive in this region right in here, place where the black holes are, where neutron stars are. We'll talk more about that. And here are things for the future, which I won't go into now, unless you ask me about them. Okay. So let me give you a little feel now. We'll go to how the detection was made. And what is in this picture is the disposition of the various detectors that are around the world. LIGO's detectors are, well, you know, one of them is real close to you. It's right here near Richland. And that's LIGO Hanford. And then there's another one in Louisiana. And the important thing is that we'll say why we have two detectors when I get to the confidence of a detection. But that was very important to us, and not even that initial proposal. By the way, if you want to visit the LIGO Hanford site, it's trivial. I mean, you can do it with a car. And if you want to go, you just have to look at the site. You go to the site on the web, find out when they are open for visitors. They're usually open on Saturdays. And if they're running, you probably won't be able to go everywhere. But if they're not running, you might be able to get right in and look at the tanks and look at all the laser. You won't be able to look at the laser, but you'll be able to look at where the house is that has the laser in it. Even the people working at the site, only a few of us are allowed to look at that go look at the laser. You need glasses, and you know, it's a pretty zippy laser. So along with that are now Virgo, which is this joint project between Italy and France, and that's right there in Italy, near Pisa. It's a much more attractive place than we have. I mean, you have a lovely town and all sorts of interesting things to look at if you go there. And then there is a test instrument, the Germans, that same German group that did all that early work that was so wonderful. They built a 600-meter system, which unfortunately for them, and I wish it was not true, they can't get into the ballgame of detecting sources. It's just not long enough. And here are things that are proposed. Kagra, which is another detector in Japan, and that's being built in a mountain in the same place where the Kamioka mine is. That's where the neutrinos were discovered. And then LIGO is given a detector. We had 3 detectors in the beginning, and one of them is being given to India to build in a completely different location. And the reason why we want more gravitational wave detectors is to be able to localize where the sources are. And I'll get to that when I show you what kind of changes it will make if you have all of those detectors. The main argument is we can't tell what we're looking at. We can't tell any astronomer with just 2 detectors, hey, go look over there. You'll see in a minute why that is. Okay, so I'll give you a little travel log of the sites. And this is a very short little clip. And this is a picture looking above at the Livingston site, the site in Louisiana. And now you'll see, I hope this runs. Yeah. And this is the site up here in Richland. Here are the beam tubes. So this is a concrete cover over the beams. And this is the end stations. That's where the masses are at the ends. And if you can, I can't see this so well, but this is the beam tube. It's just a piece of aluminum. This is a laser table near where the detection bench is. And this is a control room at Hanford here, and people learning, being taught how to run the detector. So if we go, you'll see a lot of that stuff if you go out there. Okay, so now let me get right to the detection. The conditions we had, and now let me say a little bit about how it was. Remember, the Weber incident was not a good beginning for this field. And a lot of people in this field were very worried about that we would not be able to really prove to everybody that we had detected something. So it was critical that we do this right. And what it consists of is that, first of all, if we claim a detection, we have to see it at both sites, and we have to see them within 10 milliseconds of each other. The waveforms have to be the same at both places. How much time do I have? Please tell me.
15.
What?
We do 15.
15 minutes.
15 minutes? Okay, I think I can do it. So the thing is that you have to have the same waveform at both places. the other thing is that you have a whole set of things that measure the environment, and the University of Washington contributed one of these measurements devices, a tilt meter, but none of these instruments, different seismometers, accelerometers, all sorts of stuff, measuring the environment, none of these can have a signal that is the same at the same time as the thing that you think is a gravitational wave. And then lastly, there are about 100,000 signals that come out of the instrument itself, like thing that tells you how the mirrors are pointing, that tell you how the laser's operating, and so forth, that come out. And if there's something anomalous in any of those at the same time as you see the signal, you will not accept the signal. So that's the basis of the detection. And here's what we detected. This was in that first paper and also at the news conference that you referred to, or was referred to earlier. Let me quickly say what this is. What it is this is time, on the same time on all of these. This runs from 0.2 seconds to 0.45. So it's 0.25 seconds, the whole thing. And this is the signal that we saw at Hanford after it was filtered by nothing more than the kind of tone control you have on your audio set. You know, you took the low frequencies, you killed the very low frequencies, the bass control, you turned it down a little bit. And you had a treble control, and you turned it down a little bit. So you had this mid-band, and that's all was used, and you saw this. And so what it is, this is noise, and then you began to see something that built up like that, got bigger and bigger, and eventually came to about 10 to the minus 21, just what the boys said it was. Look at that. And that signal was also seen in Livingston, which is the one in Louisiana, and they're superposed here and slid by 7 milliseconds. In other words, the signal got to Livingston first, and 7 milliseconds it came to Hanford. That tells you it came from the south. And there it is, superposed. They're not identical. There's noise in those detectors. I would not believe anything I see over here. I would not believe anything over here. That's all noise. But there's something quite systematic. And here's what theory would tell you this is, and how you get the theory. I won't say any more. There are two methods for getting the theory. We'll show you that. And one way is to do it analytically and do Einstein field equations up to a certain point. The other one is to do it numerically, and the red is doing it numerically. And so you can get all the way to all the whole signal. And it's a prediction that's made. And there's also the prediction made, the same thing, for the same parameters that comes from the theory for the signal. Both signals, these are the same. And now what you do is you take the difference between this signal and the theoretical signal, and you get a thing that looks pretty white. There's not much structure in here. That's important. And so now here is another way of representing that same thing, and that's the chirp that everybody always talks about. I don't want to play it for you because it's a bit of a phony, the way they've been doing it. But what it is this is time versus the frequency, and the frequency here is 32 hertz, and right there at the top of this is this is the bottom of the piano, and this is sort of the middle C on a piano. And this chirp runs, and where it's yellow, it's very bright, very loud, and it does something from the bottom of the piano right to where it quits at about 250 hertz. And the same thing, they're not identical because there's different noise in the two places, but this is the same chirp as seen at, this is the one at Livingston, that's the one in Hanford. And that was the basis of the discovery. Now, what is it? You can do some very simple calculations just using Newton physics to get much of this. But to get it absolutely right, you have to use numerical relativity. And that's what was done. And so here is, now this looks a little different. It's flatter looking than what you saw, and that's because this is not filtered by that tone control. That's why I wanted you to understand the tone control. That's if the detector was absolutely flat, it would look like this. And what it is this, you notice that the thing is changing frequency. They're getting closer and closer, the axis crossings. And here, and what's depicted up here is what's going on. And so here are the two black holes. They're far apart. They're oscillating around each other. They're getting closer. They've lost some energy by that time. They're getting pretty damn close. And here, whatever analytic solutions you have are still good. But when you get past that point, there's no more good analytic solutions. You have to use the numerical solutions. And bingo, these two have formed a new black hole. And this, we didn't see. We will see in the future. That's the geometry of space-time actually singing and dying out after the collision. That's not the black holes anymore. It's the geometry of space around the black holes ringing. And the thing that's sort of astounding is what's going on here in this picture right there, is that this is the velocity versus the velocity of light, the relative velocity of these two guys. And here's 0.3 the velocity of light, and the time they crash, they're moving at about 0.6 the velocity of light. I mean, imagine monster things, which we now know is about 30 solar masses moving close to for what a fundamental particle moves. That was a real shocker. And so then, let me show you what, this is a movie that was made of this by the people at both Caltech and Cornell. And this is using numerical relativity of what this collision was. And what you see on the bottom here is the waveform. And on the top here, you'll see these two things going around here. The colors indicate how much time has been changed. When it's green, it's not terribly much, but when it's red and black, the time has changed dramatically. And these little arrows that are in here are effectively the tension that somebody, if you were there, this is the tension that you would experience as you were lying there, you'd be torn apart by the gradients of the black holes. And what's happening is this movie isn't keeping constant time, as you'll see. What happens is they're now slowing it down, and you can look into the formation of the time. The time is just changing dramatically. There's the beginning of the formation of a new black hole. Now they stop the movie for a moment, and you can see this gigantic change in the time and in the space. And now you have, everything becomes quiescent. Here is the black hole, the new black hole. And now these are the gravitational waves that have left this thing at the end. And so that's, I mean, that all now is exactly calculable, which was never true, let's say, 10 years ago. Okay, so let me tell you how we do the data analysis, which is actually quite cute and important for you to know. The way it's done is there are two kinds of data analysis that were done. One was done, they're depicted in these two pictures, and I'll get them started so we don't waste a lot of time. Whoops, can I find the, oh boy, am I in trouble? Oh, no, I'm not. Okay, what you're going to see is the cross correlation of those two signals. That's the product of this times that. Move that, that's one detector, that's the other detector, that's noise and signal, that's noise and signal. And here's the cross correlation product, and it's made positive by squaring it. So there is something that stands out above the noise. And that allowed us to find the source. There it is. And what this is a picture of is signal to noise, how strong the signal is relative to the noise. And this is the probability of finding these lines, let's take only one of them, is the probability of finding another signal with only that kind of signal noise. How often will it happen at the time that we were looking? And at this point here, this thing is so strong, it's a signal noise of 20, and the probability of finding it by any time at all is something like another million years, several million years of running of that apparatus. So that's what the discovery was. And then we did it some more. And we did a different technique. In this technique, you take clean waveforms calculated, and a lot of effort went into this. A lot of people worked on this thing. And this is a different data analysis technique. You take the cross correlation between a clean waveform that is calculated, and you have many, many, many of these, and slide it over the data, and you get this. And you get a cross correlation which is very much stronger. But it is something where you have to try it over and over again, changing parameters over and over again, getting different waveforms. And now what was done, that same picture, you notice, here is the source that we saw by eye. And my God, here's another one, which we couldn't see by the other method, and maybe even a third one. Okay? And now here's the situation. The situation is, these are the three things. The one, that's the big guy we saw for sure is this. This is time versus the strain. And this is 1 times 10 minus 21. This is the one we also saw for sure, buried in the noise. It's completely different masses. This has mass 36, mass 29 solar masses, and 3 solar masses are lost to gravitational waves. And this same meaning for all of these. This is the other one. This is much longer signal. And this is the one that we think has a chance. I think it's real, but it's only about 90% or 89% real. I mean, you can't do much better than that. Right now, so I think we saw 3 events in 3 months. That's the number I use. Okay? And I won't go through this because I don't want to spend the time. I do want to show you what we can't do with 2 detectors. This is a map an astronomer would use of, and this is hour angle, and this is declination. And if you want to tell where the source is, the big one, here's sort of the error bar on the sky. That's in the southern sky. But the other, you can probably tell an astronomer, this is 100 square degrees about. And most astronomers would just look at you like you're out of your mind. You can't cover 100 square degrees to look. That's not possible. And here's the other ones. I mean, they're just all over the place. Now, why does this happen? Well, okay. Let me quickly get to that in a minute. I want to talk a little about the future and a little more about people, and then I'll be done. So these are people who are actually very important. I want to make sure they get known by you. This is now the man who was the director of Barry Barish, was the man who took over after Robbie Vogt and actually got the thing built. Here's Stan Whitcomb is the scientist who was on this thing from the very beginning of the project. He was the chief scientist of LIGO. And Barry brought this project manager who was superb. He now runs the TMT project. But he was instrumental. These two were instrumental, all the people here. And this is Al Lazzarini, who is the deputy director of LIGO at the time, and now is still a key figure in the problem, in the project. And Dennis Coyne, who was the chief engineer of the project. And lastly, this is the last picture I want to show you of people. These are people now who, as you'll see, the faces get younger as I go on, okay? Well, remember, it's a 40-year project, but it's only about 20 years with these people. So there is a scientific collaboration, the LIGO scientific collaboration, which has a spokesperson. And the first elected spokesperson was Peter Salson, who is from Syracuse. Then there was David Reitze, who was a second spokesperson, but now is the director. After J. Marks, J. Marks was the director after Barry, and then now David Reitze is the current director. So he's played two roles, and the person who's our current spokesperson is Gabi Gonzalez. And you met her at the press conference. She's wonderful. Oh, they're all wonderful. Now, I have to show you these people again, some of them. This one you've met. That's the chief scientist. But these you don't know. Here's David Shoemaker, who was effectively the manager of Advanced LIGO. And the man who was the chief scientist for Advanced LIGO was Peter Fritschel, who was you see, they're much younger. And these two people are the people at the sites who actually made the instrument go with their own hands. They were the directors for commissioning and Valera Frolov is the one who's doing this at Louisiana. And Daniel Sig is the one, if you ever go to the site, he's a very friendly guy, lovely guy to talk to. If you go to the site, you'll meet Daniel. And this is something just for fun. When I got to New York after the press conference, I had to do something there, and I was in the subway in New York, and I read, this is an advertisement in the subway. Scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet, okay? Right, and this is a few days after the announcement, okay? Then here's a thing in the New Yorker on the 12th of New York. I'm amazed by this. There's this bird, and they're talking to this guy. He says, "What's that I just heard now? Or was it two black holes colliding?" Okay? So, I mean, the fact that this got into the public conscience this way so fast was absolutely wonderful and sort of quite mysterious to me. So now let me talk a little about the future, and then I'm done. First is, if you now have if you had, this is now the angular distribution on the sky, how well could you do? And this is much better than what we did in those pictures you just saw. But this involves Hanford. Let's not worry about H. That we had two detectors at Hanford when this was going. That doesn't change this picture now that we only have one there. Hanford, Livingston, and Virgo. If Virgo had been on, we would have had a distribution on the sky which was a hell of a lot better than what you saw in that other picture. And why is that? These things don't point. These detectors do not point. What they do is you can take time differences to get and triangulate with time differences between the detector. That's how you find out where something is. Now, if you add India to this, it looks like this. Very much different. And this is Hanford, India, Livingston, and Virgo. And now these size uncertainties are sort of the size of the moon on the sky. Now, an astronomer would still sneeze at you with that, but that isn't hopeless, okay? So that's the reason we want to make more detectors. There are many other kinds of sources to look for, and neutron stars are one of them. There are very interesting sources, CW sources that continually put out radiation. People are looking for them all the time. And what I want to show you at the end here is the gravitational wave spectrum that you can expect in the next 20 years. And then I'm done. So this is now frequency of gravitational waves. This is 10 to the 4 hertz, and this is 10 to the minus 16 hertz, sort of the 1 over the age of the universe. And this is strains, going from 10 to the minus 25 all the way to 10 to the minus 5. So here's LIGO at 10 to the 4, and all the way down to about 10 to 10 hertz. And what we already know, we're detecting, we're detecting binary coalescences. We might see single CW sources. That's it. Here is another project which is doing it in space, and this is doing it there because of that gravity gradient noise, among other things. And it's at a much different frequency. The idea is to take 3 spacecraft and put them in a triangular orbit at the Lagrange point of the Sun and the Earth. And this is called the LISA project, which has been studied almost as long as LIGO. That started in 1975. And they're going to look for, well, massive black hole collisions and small black holes going into big black holes, like, for example, in the center of our galaxy. Something small black hole going into the big black hole we have in the center of our galaxy. And I want to show you something about that, which is very important. They had a Pathfinder. That was a thing that was flown just last year. And this is a thing that just tests the interferometry they would do. Here's Carsten Dunzmann, who is the German in charge of this project. Here's the thing they flew in a rocket. They put it, what was in the rocket was an interferometer with 2 test masses. And the idea was, that was in the spacecraft, and the idea was to measure the relative motion of these at the Lagrange point. They put this out at the Lagrange point. And here's what they got. Really quite spectacular. Now it's frequency again, but now different range of frequencies. Here's 1 hertz, 1/10 of a hertz, 10 minus 2 hertz, 10 minus 3 hertz, 10 minus 4 hertz. So an hour. Periods of an hour, here's periods of a minute. Very much longer periods. Here's what, and this is the acceleration spectrum, rather than the distance. They chose to plot it that way. Here's what they had hoped for as the noise. Here's what LISA needs, so it'll function properly on the basis of what people, the calculation. And here's what they got. They showed that they were already better than what they needed for LISA, the full project. It was a spectacular demonstration. Okay? All right. And now I'll talk about the other 2 things that make up the spectrum. And that is, another thing that is also going on now is to use pulsars all over our galaxy, different pulsars all over the galaxy, and using radio telescope and looking at the arrival rate of pulses from the pulsars. And if a gravitational wave goes through our galaxy, and what it does is it will cause a change in the repetition rate of the pulsars, and that's something they want to measure. And that's a way of looking at gravitational waves with periods of years to fractions of a year. And finally, there is this experiment which you know already about a good bit, but this is a very promising technique, and that is to use the cosmic background radiation, the thing that has been measured over and over again, we know the spectrum of, and look at the polarization of the electric fields that are generated by that radiation. And it turns out that if there are gravitational waves that were there from before the cosmic background was generated, in other words, almost at the time, at the instant when the universe got generated, those gravitational waves will cause density fluctuations in the plasma that we get this cosmic background radiation from, and it'll have a very special thing. It'll have a hot spot here, a hot spot there, a cold spot here, and a cold spot there. And that will give a particular pattern to the polarization that you get, the electric field polarization, from those hot spots and cold spots. And you can measure that polarization pattern. It's called a B mode. And I won't say any more than that. And people think they have already seen that. Unfortunately, they were wrong. They got messed up by dust. But there's a lot of other people, and the people who made the initial claim for this are also doing better in their experiments. I fully expect that if there are gravitational waves that come from inflation in the next 10 years, they can be found by this kind of technique. And lastly, then, this is the LSC. That's the people there are 50 different institutions in this thing with about 1,000 people, and that's the LIGO project. Thank you.
Thank you, Professor Weiss. We decided with so many people, it's a little difficult to have microphones for questions, so a number of questions were handed in when people registered, and Professor Weiss will answer a few of those.
Read them. By the way, if you want to leave, I don't feel maybe I went a little too long. I know that. But I'm just going to read the questions, and I think I can answer most of them, not all of them. Okay. The first question was, given our inability to see past the cosmic microwave background, will gravitational wave detection be able to provide us with more information about the early history of the universe than that we cannot get through electromagnetic radiation? In other words, is it possible to learn something new? I'll paraphrase here. What kind of instruments could make measurements of the gravitational radiation that came from the very earliest moments of the universe? And let me tell you the story about that. It's not very long. It's that right now, if it's the authorized amount that people think will come from inflation, none of the instruments, short of what I showed you, that those measurements that measure the polarization will measure that. LIGO will not, LISA will not, the pulsar timing will not. There is an idea that might happen if it turns out it's important enough, but it costs a lot more money than people have wanted to do. You could do something called Big Bang Observer. That's an idea that is around, and that's taking LIGO and putting it with all its bells and whistles into space, with all the high power and all the troubles you have with all the maintaining distances carefully to 10 to the minus 18 meters. See, LISA only maintains distances of 10 to the minus 12 meters. So, but you have to do much, much better than that if you want to look at the ideas that might come from the cosmic background radiation. Okay, so yes, the answer is yes to that question, but we're not capable with the current instruments to do it, and it's a bit of a struggle to get that far. The other question, the next question is, there are 4 or 5 of these. Are there any black holes near us? Yes, of course there are. We know of a big one in the center of our galaxy. 10 to the 5 solar mass black hole lives right in the center of our galaxy. What would we feel or see of the colliding black holes LIGO observed had they been colliding in our own galaxy, or even in the same arm of our galaxy? Well, I made a little number for that because that's not one you could answer right away, but you can do the answer yourself. We'll do it together. We measured 10 to the minus 21 strain from those things that were, I didn't tell you, yeah, I didn't give you that because I skipped that slide. Those black holes are 1 times 10 to 1 billion light years away, 10 to the 9 light years away. Our galaxy is 10 to the 4 light years away. Okay, now I remember that little formula with a GM over RC squared is times V squared over C squared, that gives you the H. I showed you that earlier on. So you just have to look at how far away they would be now, 10 to the 4 light years away, if it's in the center of our galaxy. So it would be 10 to the 5 times bigger. So the strain would be 10 to the minus 16. 16. That's still nothing. You don't hardly feel it. So I said to myself, when could you actually feel it? Well, if you do it in our solar system, it's still not enough. It's 10 to the minus 6. That's getting to be an awful big strain. Okay? And still, I don't think you could feel a strain that's much smaller than about 1%. I'm just thinking, here, could you measure a 1% change of your body length? I think, so you won't ever really see the strain from a black hole, these pair of black holes, unless they're right on top of you. Okay, I've heard that this is spectrum 3, I've heard that there's a big black hole in the center of our galaxy. Will we ever be able to detect gravity waves from things falling into it? First of all, it should be gravitational waves, and then maybe a little bit of a pedant for a second. Gravity waves are those things you see in the ocean, okay? Or in the atmosphere when you have clouds moving up and down. Gravitational waves are the ones we're talking about, okay? So, no, yes, LISA will actually see that. In other words, LISA is designed to look for things that are falling into the black hole in our galaxy. And LISA, hopefully, now that maybe some sense has been put back into NASA, will fly LISA. With ESA, Europeans and the Americans will fly that together, hopefully. And I think the time people are talking about is sort of order 2030. That's order magnitude. Okay, the next question, we're almost there. What are the most interesting predictions from Einstein's theories that have not been observed? Well, I don't know, everybody will have their own little things. For example, I would love to see something like geons. Let me tell you what those are. Geons are something that Wheeler invented, that the idea was that you could have light, strong enough light so that you had so much electromagnetic radiation that the mass from it was strong enough to keep the light from leaving it. It's like a black hole made out of light. It'd be interesting to see if those things had existed. They would probably look the same as black holes. That's my guess. The other thing is wormholes. And I don't know how many of you saw Interstellar. I'm just curious. How many people actually went and saw that movie? Well, Kip was a guy who had a lot to do with that movie, Kip Thorne. And there is wormhole in there that takes you from one time zone into another time zone. I don't know if we'll ever see a wormhole, but that's the thing that's predicted by the theory. So I don't know. My guess is the following. I'll tell you what my guess is we're going to see all sorts of stuff that isn't as fancy as this, but that we never thought about, that is in the universe using this new technique of gravitational wave astronomy. And it just bears to reason that that will be the case. Because every time you open up any wavelength range in electromagnetic astronomy, what happens? You'll see something new. I mean, that's when you said Galileo, or one of you people, I guess at the thing we were at. What will happen is we look at the optical sky and you see it's very uninteresting in many ways. Nothing seems to happen. You look in X-rays and you'll find out it's the most violent place you ever imagined. The universe is just busting out all over the place. Explosions everywhere. And in radio astronomy, you find the same thing. Now here is a completely orthogonal way to look at the universe. I can't believe that we know everything in the universe well enough so that we won't be surprised by a lot of things we see. So that's a prediction. Okay. And it's not my prediction, it's everybody who's in this field is very much expecting that we will see something that nobody understands. Okay, and then there was a question, what was the time, the last one, what was the time you felt most, what was the time when you felt most despondent about the LIGO experiment ever succeeding? And what did you do about it? Okay, well, I don't happen to agree with that question. And let me tell you what the story is. And other people have asked similar questions, and I'm prepared with an answer, so it isn't completely original. What it is this, and this is a piece of philosophy as an experimenter when you do science. If you work on something which you hate, and you don't like the people who are working with you, you're never going to do it. Okay? Let me say that again. If you don't like what you're working on, because you don't like it, and you wish you were someplace else, and if you didn't work with people who were convivial with you, you wouldn't bother with it. Most of us wouldn't bother. You'd get away from it. And that's just the opposite in this case. You don't think about the end result. I enjoyed fixing the problems, making things work, and making the instrument work. And yes, we didn't think that we weren't detecting anything. That wasn't the thing you thought about. And you had good buddies who we worked with. And we had a terrific time, and we still have a terrific time working with each other. That's what made the thing go. So you don't think about this. I'm telling you the truth. Okay? Good. That's it.
Thanks very much.